Okay, so far our presentations have been a bit all over the place in the sense that we had to cover a variety of topics that weren't necessarily all related to each other, but that's quite typical, especially for the start of classes in discrete mathematics and number theory as part of discrete mathematics, because to get started you need to have a certain basis of knowledge that needs to be built rather rapidly before we can start pursuing things in a bit more structured fashion. However, from here on out, we will be able to pursue things in a more structured fashion. We will have presentations that typically revolve around one theme, around one topic. And so the first theme slash topic that we're going to take a look at here are Fibonacci sequences. Those things are just something that people thought to be really cool, but they also turn out to occur in quite a few situations in nature. So let's see where they're coming from and what we can do with them. So according to the mathematical folklore, and that's really the best I can tell, Fibonacci, and by the way, Fibonacci is supposedly an abbreviation for Filius Bonacci, so son of Bonacci, in Italian. He wanted to have a simple model that describes how rabbit populations breed. Now, he made the following assumptions, and we will see right away that those assumptions aren't totally realistic. Instead of individual rabbits, he is only tracking matched pairs. And he's assuming that rabbits take 2 months to reach reproductive age. And once that age is reached, the pair of rabbits produces a new pair of a male and a female rabbit every month. Now, that's where it comes back that this is mathematical folklore, right? I'm pretty sure that Fibonacci was aware that rabbits take more than 2 months until they reach reproductive age. And I'm also pretty sure that Fibonacci was aware that even though rabbits breed like rabbits, as the saying goes, they do not produce a new pair of offspring every month. However, as a first model, this is actually pretty good because the numbers are simple. And when you talk about reproductive age versus gestation period and producing new pairs of rabbits, it's probably not too far off if you scale it, if you go in, not in terms of months, but in terms of gestation periods or so. It may actually work out rather well. So, obviously the model is simplistic. And so the times that we're using here are not the actual times. Rabbit populations are not perfectly evenly matched into male and female rabbits. And at some point in time, real rabbits also die, right? That's another thing that's not part of the model. But it turns out that the Fibonacci sequence shows up in a surprising number of real contexts, and so it is an important sequence, and this is the quickest way to motivate it. This is a traditional way to motivate it, I think. And the other thing that can be said here to anybody who is interested in modeling certainly is that a simple model often is a good start because it at least quickly gives you numbers that you can check. And if those numbers don't make sense, then you know that maybe your modeling assumptions are wrong. But if the numbers make sense and just don't scale right, then you know you're on the right track and just have to refine the model. Okay, so what's the definition? The Fibonacci sequence is defined recursively by f1 equals 1, f2 equals 1, and for n greater or equal than 3, fn plus 1 being fn plus fn minus 1. So this is a two-step recursion, if you want to call it that. And basically, if you're considering what we had on the previous panel, then basically the Fibonacci sequence tracks the number of pairs of rabbits at the beginning of each month, because at the beginning of the first month, we have one set of rabbits. At the beginning of the second month, we also have one set of rabbits, except that these rabbits now have reached maturity. And then after the, or beginning with the third month, and I think here I should say n greater or equal than 2. Yeah, I should say n greater or equal than 2. Okay, and now I am saying n greater or equal than 2. Well, when n is greater or equal than 2, I can subtract 1 off of n and not leave the realm of the Fibonacci numbers here. But basically after that I can talk about what the model is, and because none of the rabbits die, your number of rabbits at the beginning of the n plus first month will be the number of rabbits at the beginning of the nth month, plus all the rabbits that had reached maturity will have produced a new pair of rabbits, and all the rabbits that have reached maturity in time would be the number of rabbit pairs that we had at the beginning of the n minus first months. And so those that number that is being added here, that is offspring from the rabbits that have reached maturity and can reproduce. Okay, so the terms of this sequence are then also called the Fibonacci numbers, and it's a really nice exercise in two-step recursion to see what the first few terms are. F1 is 1, F2 is 2, F3 would be 1 plus 1, which is 2, F4 is 2 plus 1, which is 3, next comes 5, next comes 8, next comes 13, next comes 21, next comes 34, next comes 55, next comes, well, it keeps going like that. The next one would be 89, right? You can see where this pattern is going. Okay, so however, what you can see here is that with the recursive definition, you have to generate all the terms before you can get the term that you want, and that is rather cumbersome. So at the end of this presentation, we will also find a direct formula for the Fibonacci sequence. So yeah, computing F100 would take quite a while. Some things that we can do with the Fibonacci numbers go in the direction of pattern recognition. That is also quite important in number theory. So for example here, if we consider the first few Fibonacci numbers, which are listed here, and we compute their sums, we realize that 1 plus 1 is 2, 1 plus 1 plus 2 is 4. If I add 3, I get 7. If I add 5, I get 12. If I get 8, I get 20. And, well, that's all basic arithmetic, but now you also realize that 2 is 3 minus 1, 4 is 5 minus 1, 7 is 8 minus 1, 12 is 13 minus 1, 20 is 21 minus 1. And so that means that it looks as if when I add the first n Fibonacci numbers, I end up with 1 less than the number that is 2 ahead, right? Because if I add up to 8, I get 21 minus 1. If I add up to the 5, I get 13 minus 1, and so on, and so on. Of course, that's just a pattern that we observed, and it could fail in the next steps. So to make that a theorem, we actually have to prove this conjecture, and that's one of the ways in which mathematics works. You see a pattern, you test the pattern with a couple of cases, and then you see if you can prove it. Of course, if we say that this is the case and it turns out to be right, then because this is all recursive, it probably makes sense to prove this by induction. And, well, on the other hand, I think we're going to use summation formulas here. Well, let's see. Okay, you take the sum of the first capital N Fibonacci numbers. That's the sum j equals 1 to capital N f sub j. And that is the sum j equals 1 to capital N of f sub j plus 2 minus f sub j plus 1. Right. Because what do we know? We know that f sub j plus 2 is f sub j plus 1 plus f sub j. That's the recursive formula. Just shifted one up. And now I can split this into two sums. The sum j equals 1 to n of the fj plus 2 minus the sum j equals 1 to n fj plus 1. And now I can shift indices, right? I can only combine sums if they have the same indices. And now I shift both indices. Let's see, on the first one, I say k equals j plus 2, which means when j equals 1, k is 3. When j is n, k is n plus 1. In the other one, I say k equals j plus 1, and when j is 1, k is 2, and when j is n, k is n plus 1. And if I subtract those, well, what survives is the f sub n plus second term from this one, and the second term, which is f2, which is 1 from the first one. And that's the proof, right? Okay, so I didn't need induction here because I could work things out directly. But I could also give an induction proof. Now, let's write down a note here really quick. In order to show that a result is true, one correct proof is enough. That's it. However, it can be helpful to just analyze different ways to prove the same result, because in a class like this, we're building our arsenal of tools, and induction is a tool that is being used much more widely than re-indexing of sums, even though re-indexing of sums certainly also is very useful whenever things get heavily computational. So being able to use both is certainly not a bad thing. And yeah, so especially when it helps to familiarize you with standard techniques, it's something that we ought to do. And so telescoping sums are standard techniques, and reindexing of sums is quite common, but induction, of course, is a standard technique too. So here goes. Proof by induction on n. Well, the base step is n equals 1. And f1, well, f1 is 1, which is 2 minus 1, which is f3 minus 1. You just look at the numbers, that's it. The induction step, well, that's always where things get a little bit hairier, but what do I have? I have the sum of the first n plus 1 Fibonacci numbers. What do you do in an induction proof where you have a sum? Well, you split off the last term. So this is the sum j equals 1 to n fj plus fn capital N plus 1. Then you use the induction hypothesis, and you know that this sum is the sum of the first n Fibonacci numbers, which is f sub capital N plus 2 minus 1. And now you realize that those two add up to fn plus 3. And fn plus 3 minus 1 is exactly what you want to have when n is replaced by n plus 1 in this formula, so that's it. So, works pretty much the same way, uses the same principles, it's just that as you prove things, sometimes you see one thing sooner than another, and of course here, seeing both standard techniques certainly doesn't hurt. Okay, now, as I promised at the beginning, we want to get ourselves a direct formula for the Fibonacci numbers. Because, and we're not going to do it here, but if I wanted you to find f sub 1000, well, have fun computing the terms, right? That's something that just takes quite a while. It's still what computer scientists would call linear in time, but linear up to 1000 also takes quite a while. So, the other thing then is the arithmetic gets ugly. The Fibonacci numbers grow really fast, and so it's not unreasonable to determine a direct formula to assume that they grow exponentially as c to the n for some c. And so to find that c, we would plug c to the n into this recursion formula. This is very similar to what you do in differential equations, by the way, when you set up a solution of a constant coefficient differential equation as e to the lambda t. It's just that here the pattern is c to the n. Right. Similar to solving linear homogeneous differential equations with constant coefficients. So we take fn plus 1 equals fn plus fn minus 1. Well, that would be c to the n plus 1 equals c to the n plus c to the n minus 1. And, well, I can bring that all to one side, and I can divide off the c to the n minus 1. So I end up with c squared minus c minus 1, and that's just a quadratic formula. So that would be c1, 2 being negative b, so negative negative 1 is 1 plus minus b squared, which is 1, minus 4ac, so minus negative 4, which is plus 4, divided by 2a, which is 2. And that's 1 plus minus root 5 divided by 2, and neither of those is an integer. Well, okay, don't quite give up here, because maybe a combination of the two will give something that matches f1 and f2. Because after all, if there is a solution of the form c to the n, I can multiply that with a number, and basically all that happens is that I would factor out that number and cancel it, so that's valid. And if I have solutions with two different c's, I can also add those things up, and the summations would work out just the same. So, how does that go? Well, I take the conjecture that f sub n is a times c1, which is 1 plus root 5 over 2 raised to the n, plus b times c2, which is 1 minus root 5 over 2 to the n. And then I just work out what happens when n is equal to 1. Well, when n is equal to 1, I get a times 1 plus root 5 over 2 plus b times 1 minus root 5 over 2, which is just that. And when n is equal to 2, I get 1 is equal to 8 times 1 plus root 5 over 2 squared plus b times 1 minus root 5 over 2 quantity squared. And what do I get there? I get 1 plus 2 times root 5 plus 5. And so that would be 1/4 plus root 5 over 2 plus root 5 over 4. And root 5 over 4 plus 1 over 4 is 6 over 4, which is 3 over 2, and then it adds up to 3 plus root 5 over 2. Correct. And here again, just try to work it out mentally. 1 minus 2 times root 5 plus 5 would give us 6 minus 2 times root 5, and that's 3 minus root 5 over 2. So yeah, that all works out. Let's see, what's the next thing to do here? Probably subtracting the 2 off of each other. Yeah, because if I do that, I get 1 minus 1, which is 0. The root 5s cancel in each case, which is rather nice. And if I subtract the first one from the second one, I get 3 minus 1 over 2, and I get 3 minus 1 over 2 here also. Well, okay, so those 2's shouldn't be there. And now the 2's are gone, so just subtracting gets me a plus b equals 0, which means that b equals minus a. And if I add them up, which is what I'm doing here, I end up with, what do I have here? Okay, I add them up and divide by 2 apparently, and that's also not terribly bad to do. Okay, so 1 plus 1 gives you 2 divided by 2, and then here I get 4 plus 2 times root 5 divided by 2. Okay, so 8 times, and then I divide by 2 again, so the 4 becomes a 2. Something doesn't want to work here. Yep, something didn't want to work here. This was a computer error. The error was located between the keyboard and the chair, because what we actually do is we take b equals minus a and plug that into the first formula, right? So I've got the 1 from up here. I get a times 1 plus root 5 over 2. And then I've got minus a, because b is 1 minus a times 1 minus root 5 over 2. And now I add that all up. Let's see if I can still add. That would really be good, wouldn't it? 1/2 minus 1/2 goes away, and root 5 over 2 minus negative root 5 over 2 ought to be root 5. Yeah, so a times root 5 is what I get here. And that means that a is 1 over root 5, or root 5 over 5 if you rationalize the denominator. B ends up being negative root 5 over 5 because it's negative a. And that means that the formula for the nth Fibonacci number is root 5 over 5 times quantity 1 plus root 5 over 2 to the n minus root 5 over 5 times 1 minus root 5 over 2 quantity to the n. That formula should look familiar to you because we had worked with that formula in the presentation on numbers and sequences. And that was one of those formulas where it looked like it would keep spitting out integers, and this is why it keeps spitting out integers, because it's the Fibonacci sequence, and whenever you add integers to each other, you just get more integers. Okay, technically, however, we would need to prove now that that formula is correct, because the way the argument works was that the direction of the derivation was that if the Fibonacci sequence satisfies such an exponential type formula, then the formula must be the one that we derived. However, that's a good and instructive exercise to prove that this formula really is the nth Fibonacci sequence by using induction. And because that is a good exercise, and because we are at the end of this presentation, I certainly very happily leave you to that. I'm getting a little bit tired, as you may have noticed on the previous panel. I think I'm going to stop recording. But if you still feel like it, and I hope you do, get started on the homework on this stuff. I'll see you in the next one.